we're going to evaluate the double integral of this function here, y squared minus x over 2, over the region bounded by the curves y equals x squared and y equals root x. The answer is going to turn out to be approximately 0.0107. Take a moment though and draw the region bounded by those two curves. Pause the video to get a paper and pencil if you have to. Did you get something looking like this? This is the region bounded by y equals x squared and y equals root x. Now I'm going to rotate this around. This is actually a plot of the surface over that region. Thinking of double integration as computing the net volume, if I fill in the solid, we'll get a better idea. The portion of the object above the xy plane will contribute positively towards the net volume. The portion of this solid below the xy plane will contribute negatively towards the net volume. The fact that we know the answer, positive 0.017, means that the volume of the portion above the xy plane is slightly bigger than the volume of the portion below the xy plane. Now for the calculations. Here's a copy of the region. We can describe the region in the following way. For any value x, the minimum value for y is given by the curve, and the maximum value for y is given by the upper curve. That's true no matter which value of x you pick. So we could describe this by saying for any x, y ranges from the lower curve, which is x squared, to the upper curve, which is x. And x itself can range all the way from 0 to 1. And that would give a double integration as follows. Y ranges from x squared to root x, and x ranges from 0 to 1. Now we do the first integration. The antiderivative of y squared minus x over 2 with respect to y is y cubed over 3 minus xy over 2. And here y gets evaluated x squared and at root x. So this will replace every instance of y with root x, and that will give x to the power of 3 over 2 over 3 minus x root x over 2, and then subtract, replacing every instance of y with x squared. That'll give y to the power of 6 over 3 minus x to the power of 6 over 3 minus x cubed over 2. And this is a straightforward integration with respect to x, and I will leave out the details. You can work this out. You do get 3 over 280, which is approximately 0.0107. Now that's not the only way to describe the region or do this integration. You could also describe the region by saying that for any fixed value of y, x ranges from the left-hand curve to the right-hand curve for any fixed value of y. And the possible values for y would range from 0 to 1. And what about the possible value, the ranges for x? Well, here we have to be versatile and we have to re-express the curves in terms of as a function of y. So the left-hand curve of the region, the description is x equals y squared. And the right-hand curve, the description is x equals root y. Now this gives a double integration as follows. The function, of course, remains the same. Now x ranges from y squared to root y, and y ranges from 0 to 1. If we do the first integration, The antiderivative of y squared minus x over 2 with respect to x will be y squared x minus x squared over 4. X will range from y squared to root y. And this will give, so first replace every instance of x with root y squared root y, and this will be y over 4. And then subtract from that, replacing every instance of x with y squared. Minus y4 over 4. And this now is a straightforward integration with respect to y, and I will leave out the details. You do indeed get 3 over 280, which is again approximately 0.0107. Either way you set up the integration is valid.